Every celestial body's position is precisely determined by two special angular coordinates. Horizontal coordinates of all celestial bodies change continuously due to Earth's daily rotation. The second equatorial system remains completely stationary, so astronomers create accurate star maps. The reference point is the vernal equinox, which rotates with the starry sky.
For millennia, we've looked to the stars. But how do we actually translate that vast, twinkling canvas into a precise map? Well, today, we're going to build the very language of the cosmos, piece by piece. We're talking about the celestial coordinate systems.
So this is the fundamental problem we're trying to solve. It's one thing to see a star, to point at it. But how do we catalog it? How do we track its movement and tell someone on the other side of the world exactly where to look? For that, we need a rigorous mathematical framework. And that is exactly what celestial coordinate systems were invented to do.
So here's our plan. We'll start with the system that's most intuitive to us right here on Earth. That's the horizontal system. Then we'll move on to the more universal equatorial systems. We'll explore two different kinds, see how the Earth's daily motion affects everything, and finally, we'll bring it all together with a comparative analysis. Let's begin. Okay, let's begin with the most intuitive framework, the horizontal system. You can think of this as entirely egocentric. It's defined by you, the observer, at your specific location and at a very specific moment in time. Everything is measured relative to your personal horizon.
The fundamental reference for this whole system is what we call the mathematical horizon. Now, I want you to visualize yourself standing in an infinite, perfectly flat field. The horizon is that great circle that separates the dome of the sky you can see from the hemisphere that's below your feet. This plane, this is our starting point for everything else.
Our first coordinate is height, which we denote with a lowercase h, just as you see here. It's the angle from the horizon straight up to whatever celestial body you're looking at. This arc is measured from 0 degrees right at the horizon up to a maximum of plus 90 degrees at the point that's directly overhead. Now, the complement to height is what we call zenith distance, or z. The zenith is that point at plus 90 degrees height. It's the spot in the sky that's literally directly above your head. So the zenith distance is simply the angle measured downwards from this point to the celestial object.
This slide illustrates a really simple but elegant relationship. Since the zenith is, by definition, 90 degrees from the horizon, the height h plus the zenith distance z for any object you're looking at will always sum to 90 degrees. They're just two complementary ways of expressing the same exact vertical position.
Now for the second coordinate, azimuth. If height tells us how high the object is, azimuth tells us in what direction. So let's visualize our flat horizon plane again. We define a starting point, and in astronomy, that's typically the south point. From there, we measure the angle westward, along the horizon, from 0 all the way to 360 degrees, until we're directly under the star. That angle is the azimuth. So, with height and azimuth together, we can pinpoint any object in our local sky.
Okay, so here's the crucial point. The horizontal system is local. Your height and azimuth for a star will be completely different from someone else's in another city. And even for you, those coordinates will change moment by moment as the Earth turns. To create a universal star map, we need a system that's fixed not to us, the observer, but to the celestial sphere itself. And this brings us to the equatorial systems.
We have two primary equatorial systems. Now, both of them use the same fundamental plane, the celestial equator, which is just Earth's equator projected out onto the sky. The critical difference, as you can see, is their reference point, where they start counting. The first system is still tied to the local observer, while the second is fixed relative to the distant stars. Let's break each one down.
We'll start with the first equatorial system. You can think of this system as a kind of hybrid, blending a universal reference plane with a local reference point.
Its vertical coordinate is declination, symbolized by the Greek letter delta. This is basically the celestial equivalent of latitude here on Earth. It's just the angle of an object measured north or south from the celestial equator, from plus 90 degrees at the north celestial pole down to minus 90 degrees at the south celestial pole. This coordinate is universal for all observers.
The horizontal coordinate, though, is the hour angle, t. Now this is the local part. We measure this angle along the celestial equator, starting from the point where your local meridian crosses the equator, and we measure westward to the star's position. Because your meridian moves as the Earth rotates, the hour angle for any given star is constantly changing.
So the first equatorial system is useful for pointing telescopes, but that time-dependent hour angle makes it totally unsuitable for a permanent map. For that, we need the second equatorial system. This is the bedrock of modern astronomy. This is the grid upon which all star charts and catalogs are built. It uses the same declination as before, but its real genius lies in the horizontal coordinate, right ascension. Instead of using a moving local meridian as a starting point, it uses a fixed location among the stars called the vernal equinox. This point, where the sun's path crosses the celestial equator each spring, serves as the prime meridian of the sky, and because this starting point is fixed, a star's right ascension doesn't change. It has a permanent celestial address.
This diagram really boils it down to the core concept. Notice both systems share the same vertical axis, declination. The entire innovation is on the horizontal axis. We swap the observer's moving hour angle on the left for the fixed, universal right ascension on the right. That single change is what makes a permanent star map possible.
Now, let's synthesize all this by considering diurnal motion. That's the apparent daily rotation of the heavens caused by the actual rotation of the Earth. How does this affect our coordinates? Well, 3 of the coordinates we've defined are in a state of constant flux for anyone standing still. As the Earth spins, a star will appear to rise, move across the sky, and set. This means its height and its azimuth are continuously changing. And likewise, because the hour angle is measured from your local meridian, it too changes constantly as the celestial sphere appears to wheel overhead.
However, and this is the key, the coordinates of the second equatorial system are inert to diurnal motion. A star's declination and its right ascension are fixed addresses on the celestial grid. The grid itself appears to rotate, but the coordinates of a star within that grid do not change. This is precisely why they're used for catalogs.
So let's conclude with a direct side-by-side comparison. This should help solidify our understanding of these 3 fundamental systems.
This table really distills everything we've talked about. Notice the key progression. We move from a local main plane, the mathematical horizon, to a universal one, the celestial equator. And most importantly, we move from dynamic, observer-dependent horizontal coordinates like azimuth and hour angle to the static, universal coordinate of right ascension. This is the journey from a personal snapshot of the sky to a permanent map of the cosmos.
And that leads us to our final thought. With this knowledge, you can now answer a critical question of practical astronomy. If you were going to create a permanent catalog of stars for astronomers all over the world, which system would be your foundation? And tonight, if you were going to point your telescope at Jupiter, which system's coordinates would you need to calculate for your specific time and location? Think about that distinction, the difference between a static map and a dynamic pointer.
Thank you, friends. Strive for understanding and become wiser. See you soon.